Assalamu alaikum. How you doing, guys? Today I will be talking about or giving you an introduction on the design of reinforced concrete structures. We are going to talk about the flexural aspect of it. This is going to be a series of four recordings. This is going to be the first. In the first one, I'm going to give you just a general introduction about the methods that we use in the design, why we use steel. I'm going to talk a little bit about the behavior of reinforced concrete. And at the end, we're going to show you two examples of how to calculate the stresses in both the steel and the concrete. So with this brief introduction, let's start. Before that, I'd like to give you a historical background on the design method. We actually have two methods. One is called the working stress or the alternative design method, or the allowable stress design method. This was used from the early 1900s to the 1960s. It was quite popular back then. Actually, this method was used to design the Empire State Building in New York, so it really does have following, I guess. But then after 1960s, we came up with a new technique. So in this method, what it actually does, it takes a portion of the actual stress strain of concrete and steel. So if this is your stress strain for concrete, then I will only be working up to this range. We call this the compressive strength of concrete, or where the concrete will fail, and we usually dub this as F prime C. So when I do my design using this method, I will only be using about 0.45 or 45% of that strength of concrete. So pretty much I'm in the elastic range. Okay, so I'm not going above and beyond that value. As far as steel is concerned, so we all know that the stress strain for steel is something like that. Here being the what we call the sigma y, or the yield stress, as you guys know from strength of material. In this course, I'm gonna, instead of using sigma y, I'm just gonna use Fy, which again is my yield strength. But again, according to this method, they only use about 40% of that. So again, I'm still, which we call about 0.4 Fy. So I'm still within the elastic range of both the steel and the concrete. As far as the loading goes, I'm not using any safety factors here. I'm just using whatever normal or service loading I have, because all the safety is applied to the strength properties of both the steel and the concrete. So that's what we call the working stress. The second, the drawbacks of this method are as follows. It does not account for the uncertainty of the loads. As you know, there is some variation on the applied load through the life of its structure. So without taking any safety factors, this is not accounted for in this method. The creep and shrinkage are not accounted for the elastic calculation of stresses, and we do know that we have creep and shrinkage in concrete. And from the stress strain that I showed you, the concrete is not proportional to strain up to its crushing strength, which means, again, let me redraw this. So if this is the stress strain, and here's my F prime C, and I'm working on this range right here. So here, this portion, which gives me an added safety, I really have no clue what that value is, since I'm operating again at 45% of my F prime steel. So these are some of the drawbacks of the working method, which led to the use of the ultimate strength or strength design method. And this method we are going to use throughout this course. And we will not use the working stress method for any designs. Usually I like to talk about the working stress at the beginning, because it just gives me a feel of how to calculate the stresses, how I can explain to you the behavior of the concrete. Again, this started around 1963 and it's still in use and very strong till this date. So what's the design basis for this method? According to it, and I'm just going to read off the slide, it says that the single most important characteristics of any structural member is its actual strength. Okay, so I'm going to talk about its actual strength, not a portion of that strength, which must be large enough to resist, with some margin to spare, obviously, all foreseeable loads, which means that may act on it during the life of the structure without failure. So again, the purpose of me building a structure is having a structure that is safe, sound, and does not fail after some years. So pretty much I want my strength of the structure to be larger than the loads applied on that structure. I don't want it to be equal. I mean, if it's equal, then I'm teetering on the brink of failure, I guess. So I want it to be more than the applied loads. I need some safety again. So I want that strength of that structure be always larger than the applied loads. And we will, since this is going to be my primary method to use, we will talk a lot about that in the coming series of recordings. So why do we use steel for reinforcement? Why not aluminum? Why not some other type of reinforcement? There are some reasons for that. First one is the bond between concrete and steel prevents slippage of bar relative to concrete, so there's a good bond between the two of them. The concrete obviously mixes or provides protection against corrosion to steel, and that's more of a benefit for the steel. But the most important one to me is the similar rates of thermal expansion. Because they are similar, which means if they contract or expand, they will all contract and expand at the same rate, meaning I will not have any residual stresses or strains due to that thermal increase or decrease. Next, I'm going to talk about the fundamental assumptions for reinforced concrete behaviors. And there are actually 5 assumptions. So if any of these 5 assumptions are not there or are not reinforced, then all what I'm going to explain to you, all the theories that I'm going to talk about in the coming slides, are pretty much worthless. So we need to make sure, we need to understand what these assumptions are. So I'm going to start with the first one, which is that the internal force at any section are in equilibrium with the acting external force at that section, and that's actually obvious. Meaning, let's say if I have a beam like that and I have a distributed load, then the applied load would give me a moment of WL squared over 8, or the maximum moment that's at this section here, and this is W. We know from strength of material that my stress is equal to M times C over I. So that stress generated, or that internal stress that is generated, is from that moment, which is equal to WL squared over 8. And I'm going to show you in a couple of slides how we're going to calculate this internal moment, but it must be equal to the applied moment. So it's just pretty much static equilibrium. As for the second assumption, the strain in an embedded reinforcement bar, whether it's tension or compression, is the same as that of the surrounding concrete, which means I have a perfect bond, or I'm assuming a perfect bond between both the steel and the concrete, and which means there will be no slipping between these two materials. Actually, there's some slippage, but I will make sure, or I will enforce that I will have perfect bonding between steel, and that's when we start talking about something we call the calculation of development length, and that development length is one of the tools that I'm using to ensure that I have a perfect bond between both the steel and the concrete. Pretty much I'm saying that the strain in concrete is the same as the strain in steel. So again, this is one of the assumptions. If it's not there, I have to reinforce it, and there's a way of reinforcing that. Number 3, the cross-section that were plane prior to loading continue to be plane in the member under load, which means I don't have any out-of-plane stresses. So this assumption really is not absolutely accurate, but it is not large enough to concern me regarding my design going forward. The fourth assumption, concrete is not capable of resisting any tension and is carried exclusively by the steel. Pretty much what I'm saying here is that I will assume that there is zero stress in concrete. It does not exist for me in tension. Although we know it is there, and there are some small magnitudes. But again, I will consider them as to be non-existent. It does not influence my design. Actually, there is some small, I guess, safety there, but again, I'm not that worried about it. So here I'm assuming that I will have no concrete in the tension side. Okay, as you know, if this is my concrete section and then this is my neutral axis, so here I'm going to have compression, okay, and then below the neutral axis is going to be tension. Let's say this is for a simple beam. Then I'm going to assume that this area here does not exist. So I don't care about anything below the neutral axis as far as concrete is concerned. So although physically it's there, but from a strength perspective, stress perspective, I don't consider it to be there, and I'm assuming that all that tension will be carried by the reinforcement bars that are present here. Going to the fifth assumption, the theory is based on the actual stress-strain relationships and strength properties. If you remember from the strength of material when we were in the elastic range, we always told you that this is how if this is the neutral axis, then this is my stress, and this was my maximum stress, and as you can see, that was a linear relationship, whether this was the compression, this was tension. Now, if I'm going to use the actual stress-strain relationship, then for concrete, and I'm going to show you that again, it looks something like this. So you can see this highly nonlinear behavior, and I will be using this shape instead of this. Okay, now the equivalent simplification, I can make this shape into something more easier to deal with, but I will not show this here, and I will leave that when I start talking about the aspects of design, so you could actually feel and see what that is. But the only thing that I want you to get out of here is that I'm actually using the actual stress-strain relationship of the two constituents, and by that I mean both the steel and the concrete. So let's talk about the behavior. But before I do that, there is certain things I want you to know. So let's focus on this one for a while. So this is my cross section. So which is, if you look at it like that, so this is my cross section right here. So B is my width. So I will always be calling B as my width. H is going to be my height. Okay, so this is again the width in my design. This is the height. D now is the distance from the extreme compression fiber, which is here. This is the extreme compression fiber, to the presence of the steel bars. And I'm going to call the area of the steel bars as area S. So these H, B, and D in area of steel, you're going to be seeing them a lot. All right. Now at the location of the steel, here is my strain, which I'm going to refer to as epsilon S. Again, this is the extreme compression fiber. I'm going to call that epsilon C. FC now is my stress in the compression in the concrete. Fs is the stress in steel. FCT is the tension stress in concrete. Epsilon CT is the tension strain in concrete. Again, this is the strain relation. This is the strain, and here I have the stress. Okay, which again in strength of material we usually refer to that at sigma, and here I have the strain. Now this here shows me the relation between the stress and strain. So this part is in compression, and I need to change color here, make that black, and this portion here is going to be for the tension in concrete. So this is compression, usually referred to compression as C, and this is tension. So this shows me the stress-strain relation. So this is going to be explained to you in three ranges, I guess. The first one is what we call a low load, which means I'm still in the elastic range, and less than the modulus of rupture. So the modulus of rupture is an indication of, which I usually call FR, which is the strength of concrete in tension, which is this value right here. So this value here I usually refer to as FR. So as I'm applying the load, which is a very low load, and if I am not going above that value, this rupture stress, you will be seeing no cracking over here, which means the tension is still in control, this concrete is still in control. There are no cracks developed because I'm not going over the strength in tension for concrete. And at the same time, because again, the compression, I'm still operating somewhere over here. Okay, so again, there's no failure over here as well. So this is showing me, again, there's no cracks developed. I'm at low load, still at the elastic range, as we say. There are stresses are less than the rupture strength of concrete in tension. So what happens now if I increase the load a little bit? So if I increase the load a little bit and I go above the rupture strength of concrete, which is in this portion right here, okay, you are starting to see some cracks develop. Okay, these one in the middles, which are going upward, we call flexural cracks. Here we have a mix of flexural cracks plus shear cracks, and we will talk more about that when we start discussing about the design of shear. But for now, the flexural cracks look something like this, which is this portion right here. So if I look at the stress-strain curve, here's my epsilon C, and here's my epsilon S, which is the strain in the steel. As you can see below the neutral axis, I'm assuming that the stress in the concrete is equal to 0, which means it is non-existent, which means that all the stresses are carried, or the tension stresses are carried by the steel only. This is now my FC. I'm still in the elastic range because I'm below half F prime C. So that figure now here right there is completely gone, and I'm operating somewhere in this range right there, which is less than half my F prime C. So as far as the compression is concerned, I'm still in that elastic range. Okay, so far what we have said, if I have a low load, then I am below my rupture stress, so I will still have concrete on the tension side and the compression side. Now on the second part, I'm going now to increase the load. So by increasing the load now, I am moving beyond the rupture stress of concrete, which means I'm starting to break the concrete in tension, and this is manifested in the show of cracks. So the minute I see cracks, I will immediately assume that there's no stress in concrete tension. This is equal to 0. As you can notice, that the portions here between these two cracks, the concrete is still intact, but it's going to be a nightmare to trace which parts are cracked and which parts are not cracked. So here the assumption came that I will assume that I have no tension or no concrete whatsoever below that neutral axis, and I'm going to assume that even those parts which are shown to be not cracked to be cracked. Okay, so that goes back to one of the assumptions that we talked about earlier. Now, if you go up to the failure, so if I'm very close to failure, now I'm going beyond the working stress method. Okay, so part 1 and part 2 are related to the working stress method. After that point, now I'm going to the ultimate strength design method, in which I'm going above that value right here, and here you can see the actual stress or the actual stress distribution that I was talking about. Here also you can see that the neutral axis is a little bit higher than before. Again, below neutral axis, concrete, zero tension, zero stress. All right, so all the stress is the compressive stress, and all the tension stress is carried by my steel right here. So these are the three stages of concrete, and during class I will show you a video how these cracks develop through an actual load, through a lab experiment that we did, and hopefully we will have that maybe tomorrow or the day after. Now, ductile failure. So one of the things that I want to emphasize that we usually enforce is in flexural design, I always shoot for ductile failure. Why do I want a ductile failure? Well, ductile failure means that the failure is not going to be sudden. You are actually going to see the beam is starting to fail by using some large deformation, and that will give you at least some warning, either to clear the building, do some repair to fix the problem, so at least you will have some time to do that. If the failure was brittle, sudden, then you will have even no signs, no warning signs, so it will just collapse on the people, which is something that we do not want in our designs. Usually the crushing strength of concrete is between 0.003 and 0.004. The code usually use 0.003, and this is my epsilon C, by the way, and we are always going to use that to be 0.003. So again, I just want to emphasize that our design is going to be of a ductile nature, not a brittle nature, and we're going to do everything in our power to enforce that. Okay, and I'm going to show you how, obviously. Start doing the design. So let's start with an example, and this example, which I call the elastic case, or there is no cracking. So what he wants from us is determine the stress caused by applying a moment of 60 kilonewton meter. Let's look at the cross section. Here my width is 250 millimeters B. The height is 650 millimeters. The depth D from the top fiber, compressive fiber, to the location of the steel is 600 millimeters. I'm using 3Φ25 as my main reinforcement. Usually we call that main reinforcement. Now, Phi is usually indicative of the diameter of the steel bars. So when I say Phi 25, I mean the diameter of the bar is 25. If I say Phi 20, then the diameter is Phi 20. But this is in SI units, which is different from the British units or the US custom units, because in their units, instead of using the Phi as the indicator, using numbers. So let's say they would have number 3, for instance. So, and number 3 means that they are based on 1/8 of an inch. So number of 3 means that the diameter is 3/8 of an inch. If I talk about number 8, so this would be equal to 1 inch, which is roughly 2 Phi 25. Now, also just going off tangent here, you will notice that if you get usually from the steel manufacturer, he will provide you with the strength of the steel and also with the diameter of the bar. So Phi 25 is actually more than 25. It is about 25.1, 25.2, depending on the manufacturer. In this course, when I say Phi 25, just use the area of steel as 25. Even if for regular designs, just use the nominal diameter, because anything added to that would be just an added safety for you. But again, we will not be using the numbering system, since this is courses in SI units, not the US customary or British units. Now, other things to note here is that the F prime C, which is the strength of compressive, as you I haven't talked much about that, did I? So F prime C is usually the cube compressive strength or the cylinder compressive strength. Okay, and this is something I'm assuming that you took third year when you were, I think mostly in our labs we break cubes. So when you put that cube in that machine and you start recording the load until it breaks, so this is the compressive strength, which again I'm going to call F prime C here. It's 28 megapascal. The yield strength for steel is 420 megapascals, which is usually what we call grade 60. There's another grade famous, which is grade 40, which is in our case, or in SI units, it's 280 megapascal. I mean, okay, well, which is like we're saying for FY, I believe, grade 60 to 6 KSI, which roughly comes to about 414. But again, in this part of the world, we usually use 420 megapascals. Here I'm giving you the rupture strength of concrete, which is equal to 3.25 megapascals. Okay, so let's start with the example. So now this is the cross section that I have, and if you remember from strength, we used to call these as composite structure. So now what I'm going to do is homogenization between concrete and the area of steel. First of all, I need the modulus of elasticity of concrete, and this is equal to 4,700 square root of F prime C. F prime C here must be in megapascals or Newton per millimeter, which is the same as Newton per millimeter square. If that's not the unit over here, then you cannot use this factor because this is different from the British or the US customer units. So this will give me the modulus of elasticity of 24,870 megapascals. The modulus of elasticity for steel is 2 times 10 to the 5 megapascals or 200 gigapascals. As far as the area of steel is concerned, again, I had 3 525. This is just simply 3 times the area of 1 bar, which is pi square over 4, and this is equal to 1472.62 millimeter square. Now the conversion factor N from steel to concrete is going to be ES over AC, which is equal to 8. So now I have this perfect homogenized cross section in concrete. Again, I don't know the location of the neutral axis. As we took from statics, I can either take the moment about the top right here or take it at the bottom. It really doesn't matter. The location of the neutral axis is always going to be the same. Here I chose to take the moment about the top part. So now here, let's take this part right here, this concrete section, which was of a height of 650. This was my H. 250 was my B, and then the location of the center of that to this top right here is 650 over 2, which was H over 2. Now I'm going to take the N-1 area of steel, and we probably talked a lot about that on strength of material, so I'm not going to mention that again. So here again, this is my area of steel. This is my N-1, and then this is the distance from, which in my case here is D, and that will be equal to Y bar times area of the concrete section plus the area of the steel, which is N-1 times area of steel. From that, I will get my Y bar to be equal to 341.4 millimeters. Moving on, I can now calculate the neutral axis. Again, the second moment of area above the neutral axis, or moment of inertia. And here I'm going to use the moment of, or second moment of area about the base, and which usually is BH cubed over 3. Of course, BH cubed over 12 is the about the neutral axis. But again, since I already know the location of the neutral axis, I'm just going to take about the bases. So now here again, this is my B, this is my y bar right there for this part 1, divided by 3, plus again B times, now this is going to be H minus y bar, which is the second part right here. So this is part 1, this is part 2, and now this is simply the area of steel times d squared. This d, which you guys took in statics, is different from the d that we are using in RC1, by the way. Okay, so this distance is right here. So you could think of that distance as d, the new definition, right, minus wait a second, minus y bar. All right, okay, so this is going to be simply d minus y bar square, so forget that for now, okay, for statics, and let's use the d definition here in RC1 so that you guys don't get things confused. So by that now I was able to find the second moment of area, which is equal to 6.454 times 10 to the minus 3 to the 4. Now I'm just going to use simple stress equations, which was again mc over I. Now c is basically my y bar, I, which is the one that I calculated. The applied moment was 60 times 10 to the 3, so this is now Newton meters, and now times 0.341 meters by m to the 4. Obviously it will give me 3.117 megapascals, which is less than the f prime c 28 megapascals, so there's no failure here and everything is okay. Now I'm gonna calculate the tension stress, and that's simply again the moment times y bar, the y bar of h minus y bar, which is this distance right here. Okay, so this is simply h minus y bar. Okay, this term. So that's going to be 0.3086, and this is giving me 2.87 megapascal, which is again less than the rupture strength, which means I'm also okay, which means the concrete didn't crack, which means the assumptions that I made, that I have constant stress here, this being FC and this being FCT, and here is FS, is valid. So we are still in the elastic range for both steel and concrete. Now if I calculate the stress in steel, then this is just simply N times my bar over I. Again, the y bar here is the location of, or again, it is the d minus y bar. Okay, so this should be actually d minus y bar. So again, this is the 8, which is my N. This is the applied moment. This is the distance divided by I, which gives me 19.23 megapascals, which again is less than 420 megapascals, which again means the same. So this example talks about, or shows you how we're calculating the stresses for the elastic case. It's kind of a reminder of what you guys took in strength of material. Now I'm going to move to part 2 or range 2, which is again, I'm still in the elastic range, meaning I'm still below half F prime C, but I cracked the concrete already, which means my tension stress were larger than the rupture stress. So according to my assumption, I'm saying that anything below that neutral axis, which is right here, as far as concrete is concerned, is equal to 0, which means I only have area of steel down here. Hence, I will not have n minus 1 anymore. I will have n times area of steel. But the problem that I'm having right here, by this assumption, I have no idea how much this distance is. So to me, the location from the top fiber to that neutral axis is a complete unknown to me, which is something I need to find. Now, again, D is the distance from the compression fiber, right? From the utmost compression fiber to the location of the steel. So now I'm going to assume that my neutral axis is at some ratio of that distance D. Okay, we always know that this neutral axis is going to be above steel, and we know that this K cannot be more than 1, because then the whole thing is under compression, and if the thing is compression, it's not a flexural problem anymore, it's more of an axial compression, which we are not dealing with right now. So we're mostly talking about flexural stress, which means my neutral axis is always going to be somewhere up here. Okay, so now this K is my new unknown, which I'm assuming it is some portion, some ratio of D, to make things or life easier a little bit for me. Okay, so if I want to locate the neutral axis, all I have to do is just take the moment about that neutral axis. So if I do that, or before I do that, I just want to talk a little bit about the stress. So down here, this is stress, Fs. Okay, I'm going to convert that to a tension force, which is just simply Fs times the area of steel. This is now my compression force, C, right? And this is my triangular shaped distribution of the stress in concrete. This is now Fc. The location of that compression force is going to be, again, this distance right here, which again is KD. It's going to be located 1/3 of that cross section. Okay, so this shows me now the compressive force and the tension force. Compressive force is simply the area under this triangle times this distance B. Now, going back to the location of neutral axis, again, I'm just going to take the moment about the neutral axis. So for the top part, okay, let's call that part 1, which is this right here. It's going to be, again, B is in that direction. It's going to be B times the distance. No, I'm sorry. This is my B right here. Okay. So this is going to be a B times KD times KD over 2, because the location of the centroid of this is going to be KD over 2. And then the moment from the area of steel is going to be N area of steel times D minus KFD, which is this distance right here. So D minus KD is this. Okay. Now, before moving on and trying to solve for K, and I'm going to introduce now something for you, which is I'm going to call rho, which is a very important factor, which we are going to call the reinforcement ratio. So rho is simply the ratio of the area of steel to the overall cross section of concrete, which is B times D, where D again is the distance from the compressive concrete top compressive fiber to the location of to the center of the steel bars. Okay, so what's the significance of rho actually? Well, it has two. First one, from a mathematical aspect, is it ties the three unknowns together. Usually when you go into a design, you will not know the or if it's a design from scratch, I will say, you will not know the cross-section dimensions, which are my B and H, and the area of steel. Okay, so usually I shoot for D because that's more important to me, because this usually represents to me the moment arm for steel. And if I know D, then automatically I will know what H is, and I will show you that down the road. So again, from a mathematical point of view, I'm able to connect the three unknowns together. From a physical point of view, which is much more important to me, is this row, this here, is an indicator of how ductile my concrete section is. Okay, so this row usually controls the ductility of my cross section or of my concrete beam. And usually when I do my design, I like to be below a certain ratio. If that ratio is achieved, then I'm having a ductile failure. If I'm above that ratio, then I'm more into the brittle realm of my failure, which is something I do not want to be in. Okay, so again, this is the beauty of this ratio. It gives me an indication of the ductility of my design, and that's why I'm introducing it here. So again, now I'm going in and replacing the area of steel with rho BD, okay? And in doing so, this is what I'm getting. Again, reorganizing everything in terms of K and rho. Then I will find K equal to minus 2n plus rho plus or minus square root of 2n rho squared minus 4 times minus 2n rho over 2. And since K is always a positive ratio, then this is the value that I'll be concerned about. Okay. Now again, there is another introduction to the J variable, and that's actually a holdover from the working stress method, because you usually find back in the days when engineers used that technique quite a lot, tables of K and J and what the appropriate D would be and what the appropriate area of steel would be. But again, D is again a ratio of D, and it is the distance between the compression force and the tension force. So if I know what my D value is, and then I know what K is, then then this distance here is equal to D minus KD over 3, which means I can the value of J to be equal to 1 minus K 3. Okay. So now from that I can find what my compression force is and what my tension force are. Now tension force is simply the area of steel times Fs, and then the compression force is actually the area of this triangle times the width B, which is going to be equal to 1/2 Fc times K phi D phi times B. Okay. Now again, equilibrium requires that the couple constituted by the two forces C and T be equal to the external bending moment. Again, this was one of my assumptions. Then moment is going to be equal to T JD, and moment from the compressive force is going to equal to C times CJD. Again, because remember, this is a couple. Always T is equal to C from equilibrium. These are one of the most important facts that we are actually going to use in deriving a lot of things for the design in the coming recordings. Okay. Again, so T is equal to C due to equilibrium, and then the moment is either C times JD or T times JD is going to be the same. But by using these different definitions, I can find the stress in steel and I can find the stress in concrete. So Fs is going to be simply the moment divided by area of steel JD. As far as the compressive strength is going to be equal to 2m divided by kgbd squared. You don't have to memorize any of that. Usually it will be provided to you through a sheet anyways. So now, having derived the stresses in the steel and concrete, we are going to, before that, I'm going to have some general notes about the working stress. So what the previously derived equations that we have given so far are only valid for rectangular cross-section, which means circular cross-sections are not valid. I have no axial loads, which means I'm only talking about pure bending. So if I have any axial load there, again, the derivation of these stresses are not correct. I have no compression reinforcement, which means if this is my cross-section here, again, here's my neutral axis. Here I'm having the tension reinforcement. Sometimes, and this is what we call doubly reinforced, I will require some reinforcement in the compression side. As you can see, when we did the derivation, those were not present. So if they are present, again, I cannot use these equations that I driven before. One more thing, as you can see, I went all the way back to the 95 code, because after that code, this working stress is not, it used to be mentioned as an alternative method, but then it just got, I think after the 08 code, it's not mentioned anymore. But again, for that, Fc is usually less than 0.45 F prime C. Fs is usually given a value which was 170 megapascal if I had grade 60 steel. Okay, again, no provisions are available in the new. Actually, from 11 onward, there are no provisions for the working stress method. Okay. Now let's do another example. Here, I want to determine the stresses caused by applying a moment of 120 kilonewton meter. I'm using the same cross section. So by using the same cross section, the only advantage here I have is I already know or I already found the stresses for the elastic section, or where I assume there was no cracking. Okay, again, if I go to this example beforehand and I have not done the 61, I have no clue if the concrete is cracked or not. So the only way for me, if it's cracked or not, I actually have to find the stresses in the tension fiber first, and then make the decision whether it is cracked or not cracked. And so that's what I'm doing. So now again, to calculate FCT, since I already calculated that from the previous example, and this also was from the previous example, I'm just plugging in the 120 kilonewton meter, which is giving me 5.74 megapascal, which is larger than the cracked or the rupture stress. So again, the section here is cracked. So since it's cracked, now I'm going to use the K values or K equation. From that, again, K is equal to minus n rho plus square root of n rho squared plus 2n rho. My y bar is simply KD. N is equal 8 as before. Rho now is the area of steel, which was the 3,525. Divided by B, which is a 250, divided by D, which was 600, and this will give me a value of 9.817 times 10 to the minus 3. Remember, this is a dimensionless value. By plugging rho and n in this equation, I'm finding K to be 0.325, and Y bar is equal 195.3, and the neutral axis is equal to 2.55 times 10 to the minus 3 m to the 4. This value is correct. Usually I get a lot of heat on this value. That's not correct. Well, no, it is the actual value. Although you don't need it, but just as an exercise, you might want to know how to get this value. So now, calculating the stresses. So again, from the previously driven equations, which again you don't need to memorize, Fc is equal to 2m times K phi J B D square, and this is giving me 9.2 megapascals. The stress in steel now is equal to M over area of steel times J times D, and this is giving me 150.5 megapascal. So by doubling the moment, again, went from 60 to 120, we noticed that we had cracked the concrete. So FC increased by 3 times. So again, there is no linear relationship. So it was not doubled by 2 times. FS also increased by almost 8 times. So again, it was not a 1-to-1 ratio. So this is just going from the non-cracked section to the cracked section. The neutral axis moved up, and the neutral axis actually, the second moment of area, but the neutral axis was reduced to 1/2 time, which means it will have some influence on deflection, and by that I mean the deflection will increase. Obviously, if you increase the load, the deflection would increase. So this conclude my first recording on this series. So you guys stay safe, and we'll see you in the class hopefully sometime this week.